Okay. The topic today is the specialized hardware for efficient machine learning. Over the past few weeks, the professor who introduced many machine learning architecture, machine learning algorithm, and some quantization compression technique. And as the model size increase, the computational cost also increased, right? So some research, they try to develop specialized hardware for machine learning algorithm. They want to make the machine learning, the deep learning algorithm could run on the hardware platform more efficiently. So this is the outline today. The first item, I will introduce the challenge for today's computer architecture, the monument architecture, and and then I will introduce two specialized hardware design, the systolic computing and the processing in memory. Okay. This slide shows the monument architecture. Okay. The monument architecture proposed by John Monument in 1945, and the foundational component uh, it's the foundational component for the modern computer. The monument architecture include the input device and the output device and the central processing unit. And the most important feature is the memory unit. The memory unit will hold the data and the program. So when you need to run a program, you will load the program to the processing unit and also fetch the data you need to the processing unit. And this slide shows an example to run the image classification in von Neumann architecture, the model weight and the program instruction. The program instruction maybe like the PyTorch framework or TensorFlow framework, they will store in the memory, and the processor will fetch the weight and the activation layer by layer for the MAC operation. The MAC operation is the multiply and accumulate operation. And the intermediate feature map will return back to the memory after you compute the result, right? So for large model, the communication between the you will have a lot of traffic between the memory and the processor, right? So as the model increase, as the model size increase, the bottleneck will be the memory. And this slide shows the explosive growth in model size. The x-axis is the time from 2019 to 2023. The y-axis is the model size, the parameters. So you can see that in 2019, the model size just 100 million parameter. And after 2022, the model size increased to 500 billion parameter. So we can expect that in the future, the model size will continue to increase, right? So the memory bottleneck is an important issue if the model size continue to increase, especially in the von Neumann architecture, because in the von Neumann architecture, you need to fetch the weight from memory to your processing unit and do the operation, do the MAC operation, and write back the result to the memory unit. So you can image that for a prompt in the large language model application. For a prompt, maybe you will have hundreds or thousands tokens output, right? So it means one token you need go through the whole model once. So if you have hundreds tokens output, thousands tokens output, the communication between the processing units uh, and the memory unit will have a lot of data traffic. And some research, they try to break down the energy consumption. So on this slide, show the energy consumption breakdown for different operations, the add operation, the register file, access operation, the multiplication, and the SRAM cache, DRAM memory movement, energy consumption. So you can see that the energy consumption of the DRAM is larger than others, right? It's because the DRAM is an off-chip component. It's outside the CPU. So you need to you need consume a lot of energy to communicate, to move the data between the CPU and the DRAM. So under the von Neumann architecture, frequent data movement is inefficient. So this slide shows the key issue. The data access is a major bottleneck, and the data movement, energy consumption dominate the computation. So that's why we need a more efficient design for the machine learning, because the von Neumann architecture suffer from the memory bottleneck and the high energy data movement. So this driving the research toward specialized hardware design. And today we will introduce two hardware design for efficient machine learning computing. The first is the systolic array. Maybe you have heard this because it deploy inside the TPU, the Google TPU is based on this architecture, the systolic array. And the other item is the other technique is in memory computing. In memory computing, the key idea is shown on this figure. In the middle is the conventional approach. If you want to, the pink area is the processing unit. The blue area is the memory. If you want to, if we need to do the computing, you need to load the data from the memory to your processor, right? And when you finish your operation, you write back the results to the memory. And in memory computing, or some research call it processing in memory, the concept is that we move the computing unit, the logic unit to move the unit to the memory. So we could directly do the computing inside the memory. This is the key idea of the in-memory computing. Or some research call it processing in memory. And the key idea for the systolic array is load the data once and reuse the data many times. Compared to the von Neumann architecture, we load the data once and we finish the operation. We write back the results to the memory, right? And the systolic operation, the idea is reuse the data. They just loaded the data once, and the data will propagate on these computing units. And when it finish the operation, they just write back the final result to the memory. Okay. Okay, let's start the systolic computing. The systolic, this term is from the medical field. The systolic, it means when the uh, heart when the heart muscle contract, it pump blood through the body, right? And just like shown on this figure, when your muscle contract and it pump the blood through the body, and the diastolic, it means your heart relax and it refill your heart refill with the blood. And in systolic computing, the memory just like heart and the data just like blood, and the processing unit, processing element just like the cell. So when your heart contract, the blood will throughout the body. And in systolic computing, the memory will push the data, make the data go through the processing element. And when the processing element finish, when the data finish its operation, and you write back to the memory. The systolic array was proposed by Dr. Kong in 1982 in CMU. And the concept is the data flow from the computer memory in a rhythmic fashion and passing through many processing elements before it returned to memory. The key idea is data reuse. In the figure, the upside is the traditional approach. Your processing element, you fetch the data once and do a calculation and write back the result to the memory. And when you needed the data again, you fetch it again. And in the systolic array, in the systolic computing architecture, there are a lot of processing elements. They have a processing element array, and you just need to fetch the data once, and the data will propagate, will go through the all processing elements. And when you finish the computation, you just write back the result to your memory. In the following slides, we will go through some example for the systolic operation. And Dr. Kong proposed a family of systolic design. There are two types. The semi-systolic convolution array with global data combination, and the other one is pure systolic convolution arrays without global data communication. The difference is with and without the global data communication. The global data communication is being, for example, here the semi-systolic array. Here, this figure, each processing element connect to a global buffer. So the global buffer connect to each the processing element. So the implementation cost is higher than the pure systolic array, right? Because you need a global buffer, and the global buffer have a bus connect to each processing element. But this design is more flexible than the pure systolic because you could change you could change your input anytime because in each cycle you could determine your data from the global buffer to the processing elements. And the pure systolic is when the data uh, propagates on this array, you could not change it. You just make the data uh, propagate on this processing element. And yeah, in each type, they have different design. And yeah, I will show this this design. Okay. Okay, and this slide shows the semi-systolic operation with the global data communication. In this type, semi-systolic have three designs: the B1, B2, and F1. The B is mean broadcast, the broadcast input. It means have a global buffer to broadcast the input, and the F is mean the fan-in results. It means have a adder, and the results will fan in, and the result will feed into the adder and get the final result. And uh, different type have different data movement policy. For example, the design B1 broadcast the input and move the result, propagate the results between among all processing elements, and the model weight stay in each processing element. And the B2 uh, it will move the weight. The weight will will rotate uh, among all processing elements, and the results will accumulate. The results will stay in the processing element. And yeah, the F1, this type, the input will the input will propagate to each processing element, and it will do the multiplication, and then the adder will do the accumulation, and you can get the final result. And in each figure have its the bottom side have its different definition. For example, the design B1 here, the definition for each processing element is it have input X in and Y in, and the weight is on the processing element. And the definition of this processing element is you will do the multiplication, the weight, and the input, the X, and add with the Y in, and then propagate the result to the next processing element. Okay, let's go through more detail about the execution flow, and I will use this I will use the 1D convolution as the example to go through the execution flow. The definition of the 1D convolution is on the left-hand side here. And I think you could see the right-hand side. It's easy to understand. For the 1D convolution, you have an input array, right? 1, 2, 3, 4, 5. And you have a convolution kernel, and you do the 1D convolution operation. So you do the multiplication and the accumulation and store the results here. And you shift the kernel and do the convolution again. So you have the second result. Yeah, so yeah, this figure shows the 1D convolution. Okay, and this slide show the execution flow of the systolic array to the semi-systolic. This slide shows the semi-systolic with the global data communication. This design, the B1 to do the 1D convolution. In this design, you will broadcast the input and move the result, and the weight stay on each processing element, right? So here you have an input. The input is x1, 2, 3, 4, 5, and the kernel is w1, 2, 3, and the output is here. We expect to get the convolution result, the 1D convolution result here. And the definition I just mentioned, the definition is shown on here, the figure B. And this table is the content of each cycle. I dump the content of each cycle. For example, here the table have cycle 1, 2, 3, 4, 5, right? And the first cycle, the global buffer will broadcast the X1 to each processing element. And the second cycle, the global buffer will broadcast the X2 to each processing element, right? Yeah. And the cycle 3 broadcast X3, and the processing element 1 out. Because of the definition is here, so you can see that the processing 1, the output of the processing 1 is the x1 uh, times the w1, right? Follow this definition, and the the P1, the output will propagate to the next processing element, the PE2. So for the PE2, the Y in for the PE2, the Y in is Y in for the PE2 is the PE1 out, right? So the PE1 out will propagate to the processing element 2, and on the PE2, it will do the now the second cycle, the broadcast is X2. The broadcast is X2, and on the PE2 is W2, the weight. So it will do the X2 times the W2 and add with the output from the PE1. So the PE2 out, the PE2 output is here. X1 times W1 add the X2 times W2. And so next step, the third cycle. The third cycle, the PE3, the Y in is the output from PE2, and you will add with the X3 times the W3. So here we get at the third cycle, we get the convolution output, the first element of the convolution output. So follow this step, we could get follow this step, we could use the systolic architecture to do the 1D convolution. And we just fetch the data once, and the data propagate on the processing element array. And finally, from the right hand from the processing element 3, the output, we could get the result. Yeah, so this is the execution flow to show how to use the systolic concept to do the 1D convolution. Okay. And in the paper, the systolic array, they also propose other architecture in the B2 type. Yeah, it also broadcasts the input and move the weight. The weight will rotate among the all elements, and the results will stay in each processing element. And for example, here the table, the cycle 1, 2, 3, 4, we broadcast x1, 2, 3, 4, and the weight will rotate uh, among all processing elements, right? Here, W1, W3, W2, and in the next cycle, it will rotate. W2, W1, W3, and next cycle, rotate again, W3, W2, W1. And the definition is here. And in this design, the result will be accumulate on each processing unit. And for example, here the Y1 here is mean the Y1 register in the processing element 1 here. The Y1 will follow the definition. The Y1 will be X1 times the W1, and at the next cycle, the second cycle, because the weight will rotate, so the input for the PE1 for the Y1 is W2, and then in the previous cycle we have X1 times W1. So in the second cycle we will accumulate the X2 times W2 accumulate the X2 times the W2 on the Y1 register. Yeah, because second cycle the broadcast is X2, and because of the weight rotator, so the weight input is W2, and at the third cycle we get the first element of the output of the convolution output. Yeah, so follow this step. We also could use this type to finish the 1D convolution operation. And what is the difference between these two designs? The B1, the weight stay in the processing element, right? And this B2 type, the result stay in this element. It's depend on if you BWidth if your BWidth for the results is larger than the weight, maybe you will prefer to state the results on each processing element, because if you move, because you need to build the enough bandwidth for your data. So if the data bandwidth, the memory bandwidth for the movement data is very large, maybe you need you have higher cost to handle this. Okay, and the last one design for the semi-systolic is the F1 type. Yeah, here the definition showing here, the Z out is the multiplication, W1 times the X in, and the Z out will be accumulate by the adder, and to get the final result. So at the third cycle, inside each the weight is stay in each processing element, right? W1 stay in PE1, W2 stay in PE2, W3 stay in PE3, and the input will propagate from the left-hand side to the right-hand side. And at the third cycle, x1 is the x1 is the input of the PE1, x2 is the input of the PE2, and x3 is the input of the PE3, and we could get the convolutional output, the 1D convolutional output. Okay, so in previous slide, we introduced the semi-systolic convolutional array. The semi-systolic convolutional arrays with the global data have a global buffer and broadcast the input data to each processing element. And next, we will introduce the pure systolic convolution array without global data communication. Also here, on the slide, we show the pure systolic operation without global data communication, the design R1 type. The R1 is mean the result accumulate on each processing element, and input and weight move in opposite direction. It means the model weight will propagate from the right-hand side to the left-hand side, and the input will propagate from the left-hand side to the right-hand side, go through the all processing element arrays. And yeah, between each input, it need add a dummy cycle. You need add a dummy cycle between each element. It means, for example, at the first cycle, the x2 is the input, and the next cycle, no input, and the next cycle, the x3 is the input. So follow its definition and the rule, we have a table. I dump the content of each cycle, and the weight in here show the weight in and the x in for the PE1 So we can see that the weight in the further cycle is W1, and because between two weight we need a dummy cycle. We need a dummy cycle here. So here is a dummy cycle. And the third cycle, the W2 will be the input. And next, a dummy cycle. And then W3. And yeah, so the X input for the X input for the PE1 is the same. Have a X1 in dummy cycle and X2 dummy cycle and X3. So follow the definition, the Y1 will be the W1 times the X1. And the third cycle, the results will accumulate on the Y1, right? So at the third cycle, the Y1 already have the X1 times W1, and you will do the X2 times W2 and accumulate the results on the Y1. So at the 5th cycle, we get the first element output of the convolution results. And why we need add the dummy cycle? That's because why we need and insert a dummy cycle between each element. That's because we need to ensure each input and each weight can meet each other, can arrive at the same processing element. For example, if we do that, the left-hand side, if we do that without dummy cycle, at the first cycle, in the P1, the W1 could do the multiplication with the X1, right? And we don't have dummy cycle. So the second cycle, the weight will shift one element, and the input also shift one element from the left-hand side to the right-hand side. So the W1 could not meet the X2 to do the multiplication. So if we have a dummy cycle here, the further cycle W1 times uh, X1, and the second cycle, the W1 uh, could do the multiplication with the W2 in the processing element 2. So that's why we need to insert a dummy cycle between each element. Also, yeah, in previous slide we showed the R1, and then this is the R2. The difference thing between R1 and R2 is in the R1 you can see that the utilization of each processing element just half, right? Just 50%, because cycle 1, cycle 2, the Y1 is the same result. The cycle 3, cycle 4 is the same result. So the utilization is just half. And how to fully utilize the processing element? Make the processing element could be busy at every cycle. This paper, they propose this approach. The results state and the input and weight move in the same direction, but at different speed. The key is the different speed. The different speed is mean um, the weight and the x, the input and the weight, you will propagate from go through the all processing element, right? But they run at different speed. And the definition, why they have different speed, the definition is here. At each cycle, the x input will directly propagate to the next processing element, and the weight have a register inside the processing element, and the weight will keep at the processing element at one cycle, and the next cycle it will propagate to the next processing element. And why we need the input and the weight run at different speed. This slide show the reasons. In processing element 1, we don't have delay because the input for the processing element 1, W1 and X1, they do the multiplication, right? And for the processing element 2, if no delay, and we will do the W2 times W2 multiplication with the X2, but actually this could do in the processing element 1. And if we delay one cycle for the PE2, the W1 could do the multiplication with the X2. And for the PE3, the weight will delay 2 cycles. So the W1 could meet the X3 and do the multiplication with the X3. So also, here is a table to dump the content of each cycle, and to dump the content change. And at the third cycle, we could get the result, the first element of the conversion result on the PE1. If you want to trace the step, I have uploaded the slide on the canvas, so you can download it. And yeah, if you need, if you want to trace the cycle, the content of each cycle. Okay, so yeah, the input and the weight run on different speed. So the W1 could each weight could meet all inputs. Also, yeah, this is the W1 design for pure systolic. The weight stay and input and the result move in opposite. The weight stay in the processing element, and the result will propagate from the right hand side to the left hand side, and the input propagate from the left hand side to the right hand side. So the further cycle x1 times the x1 times the w1 and the results, and follow the definition, the result will be propagate to the next processing element here and accumulate with the x2 times w2 and then propagate to the uh next process PE3 and to get the final result. Yeah, to solve the utilization problem, yeah, the same. The input and the result move in the same direction, but at different speed. So this is the W2 design. This is the W2 design. And yeah, in previous slides, we show how to do the 1D convolution by the systolic architecture, right? But actually, in a fully connected layer, we need do the metric multiplication or vector matrix multiplication, just like here. You have input X and you have a weight metric, and you want to do the vector metric multiplication or metric multiplication to get the results. And in the following slide, we will show how to do that by the systolic architecture. Also, the convolution operation, the 2D convolution operation also is an important operation for the image pattern recognition, right? And how to do the convolution on the systolic architecture. And actually, the convolution operation can be unrolled to form and metric operation. So, yeah, from this slide, we can know that actually we just need the uh, metric to metric multiplication, and we could use the metric to metric multiplication to simulate the convolution operation. So this slide show how to do the matrix multiplication on a 2D systolic array. There are two types of the 2D systolic array: the output stationary design and the weight stationary design. The output stationary design, the output, the result accumulate, store on each processing element. And the weight stationary is meaning the weight store in each processing element. Uh, these two types is depend on if you need to if your weight is fixed. If your weight is fixed, you always use this weight. Maybe you prefer the weight stationary. And if you your weight change at each time, you dynamic change your weight, maybe you will prefer the output stationary design. Okay. This slide show the output stationary design for the multiplication on a 2D systolic array. Here the formula is the matrix multiplication definition, right? And we expect to get the result here. And the figure here show the definition of each processing element. The key component is inside the processing element. They do the multiplication. And accumulate the result inside its processing element. So, for example, for the y11 here. For the y11, we have the x times x and weight multiplication, and for the y11, we expect to get the w11 times x11 add with the w21 times the x12, right? So here the x11 times the w11 and the result will accumulate inside the processing element. And the second cycle, the w12 will times the w21 and accumulate with previous results and store in the register on the y11. So yeah, in this way, after 3 cycles, oh no, because this after 4 cycles, we could finish the operation to get the whole result. And this slide is the weight stationary designs. The weight stationary designs. In the weight stationary design, the weight stay in each processing element, and the input and the output move. The input move from the left-hand side to the right-hand side, and the results will output from the bottom side. The definition of the weight stationary is shown here. It will do the multiplication and the input times with the weight, and then accumulate with previous output. Right here, the red line, it will add with previous result and propagate it to the next processing element. For example, for the x11, the second cycle, the x11 will times the w11 and propagate the result, the w11 times x11, to the next processing element and add with the x12 times the x12 times the w21 and output the final result. Yeah, this is the weight. This is the floor for the weight stationary. And so, yeah, in previous slide, we show how to use the systolic array to do the matrix multiplication, and we have the output stationary design and weight stationary design. And maybe you could find that we need to skew the data format, right? We need skew the data. Why we need to skew the data? Because we need to ensure the data can meet on the correct processing element. For example, here for the y12 operation, the result, the y12, we need the w12 times the x11, right? So at the first cycle, the x11 will in here, y11, and the next cycle, the x11 will in the W12. So we need to make sure W11 could meet the W12, and then they can do the multiplication. So we need skew the data. Okay, so yeah, in previous slide we introduced the systolic array operation to run to do a 1D convolution operation to do the matrix multiplication. And this slide show the power efficient between the GPU and the TPU. Yeah, the media GPU, yeah, this model is very new, right? September release date September 2025, and the TPU V7 also very new, April 2025, April 2025. And for the 14.8-bit operation, the TPU is more efficient than the GPU. Yeah, inside the TPU is the systolic array implementation. So yeah, recall again, the systolic computing, the concept is the data flow from the computer memory in a rhythmic fashion and passing through many processing elements before you return to memory. And the key idea is the data reuse, right? The data propagate on each processing element, and we could directly reuse the data. And the traditional approach is right back to the memory. And when you need the data again, we need to fetch it again. So this is the difference between the systolic design compared to the previous monomer architecture. Okay, uh, let's take a break. Now it's 7 o'clock. Maybe we back to the 7:15. Okay, thank you. Kieran, can you see my screen?
Yeah.
Okay, thank you. Okay. In previous class, we introduced the systolic array, right? And this class, I will introduce the processing in memory, the PIM, and there are two types implementation for the processing in memory, the digital PIM. The digital PIM and the analog PIM. Okay, why we need processing in memory again? Because the monomer architecture, the traditional monomer architecture, suffer from growing memory bottleneck and high energy data movement. So yeah, we try to some research try to design specialized hardware. In previous class, we introduced the systolic, and this class we will discuss about the in-memory computing, the processing in memory, and the the processing in memory have a digital implementation and the analog implementation. The digital in memory computing is use the digital circuit for computation. It's just like in the figure, the upside is a traditional von Neumann architecture. The left hand side is the processing unit, and the right hand side is the conventional memory. So once you need to do the computation, you fetch the data from the memory to the processor, to the processing unit, and do computing, and then write back the result to the memory. And the digital in-memory computing it's mean just move the computing logic, the computing logic unit to the memory side. And then we could do the computing inside the memory. It's easy to integrate it with the existing system, right? Because yeah, it just move the computing logic from the processor to the memory, but it lower the energy efficient than analog PIM. In the analog in-memory computing, it use the analog behavior to implement the computation. In the analog, they leverage some characteristic from the material. For example, the ohmic's law. The formula show on the slide. The I is the current. I here is the current. I is equal to the G times V. The G is the conductance. The conductance is the one divided by the resistance value, and the V is the voltage. So have this formula, we could expect that we could do the multiplication, right? Because the I current is the G times the V. The relationship, the formula is that. So we could use this formula to do the multiplication. And it's more energy efficient and parallel. But because it's a analog operation, it's a analog computing, so they have some noise and conversion overhead, because I think the logic operation is more mature than the analog computing. Okay, so let's start to introduce the digital in memory computing. Yeah, on the slide, the left hand side is the von Neumann architecture. The right hand side is the processing in memory, and it's the digital processing. It's the digital implementation. It's just like move the logic unit from your processor, CPU or GPU, to your memory, and the inside the memory, the processing in memory, the bandwidth is very large than the bandwidth between the CPU and the DRAM. So yeah, inside the memory, the bandwidth between the memory cell and the logical units is very large. So you could do the data movement by minimal energy consumption and very quick. This slide is an die uh, the photograph from an product, the PIM product. It's a 4 gigabit die with 16 processing units. So from this figure, we can know that, yeah, in the PIM implementation, processing in memory implementation, it just put uh, a processing unit, many processing units into the memory, and the processing unit could directly access the bank, the memory bank, access the data, and do the computing, and write back the results to the bank. So yeah, let's uh let's uh check the processing unit here. From the on the screen, you can see that inside processing units, uh, they have a multiplier do the multiplication, and the adder tree to do the accumulate, and you can get the MAC result, right? The multiplication accumulation result. And in the processing unit, it also implements the activation function. So yeah, it's a hardware implementation for the activation function. So you could do the activation inside the processing unit. For example, if you need to do a Mac operation inside the memory, you don't want to move the data to the CPU or GPU. You just want to do the Mac operation inside your DRAM, inside your memory, and your memory have processing units, and the processing unit will fetch the data from the bank, from the memory bank, and the buffer, and do the multiplication accumulation, and then you could get the Mac output. And yeah, also you could load the BIOS from your memory bank and add the BIOS to the Mac results. And then in the processing unit, they also implement the activation function. So you could do the activation inside the processing unit and write back the result to the memory bank. So yeah, the previous slides show the digital version for the processing in memory. The concept is yeah, just add a processing unit inside the memory, and you don't need to move the data out. You just do the um, Mac operation inside your memory, because the neural network, the deep learning network, have a lot of metric multiplication, right? And metric multiplication is the multiplication and the accumulation. So you just implement this Mac operation inside your memory, and you can use this hardware to uh, do the inference acceleration. And next, we will introduce the analog in memory computing. The analog in memory computing. The constant elements have the charge-based memory and resistance-based memory. And we will show some example how to use this kind of memory. We will show how to use the SRAM to do the bitwise multiplication, and show how to use RN to do the matrix multiplication. Yeah, the analog in memory computing is uh, they just use the memory cell, to do the computing, not implement the logic in the memory. They just use the memory, the material characteristic to implement the operation. The constituent element have the charge-based memory and the resistance memory. The charge-based, it means how to represent the data. They use the presence or absence of charge to represent the data 1 or 0, and the resistance-based memory is use the atomic arrangement or orientation to represent the the data stored in the memory cell. And this slide show the example. Use the SRAM to represent logical 0 and 1 on the the SRAM cell have two NOR gate, right? So we can know that because the NOR gate is here is a NOR gate cycle connection. So the state 1 on the left hand side will be a keep in 1, and the right hand side will keep in 0. And once the wall line to be select, the mouse will be turned on, and we could read the result by the bin line. Yeah, the right hand side is a logical 0. Here, the content of the SRAM is logical 0, and the wall line turned the mouse on, and we could read the results from the bin line. And this slide shows how to do the logical operation using SRAM. The logical operations mean the AND operation, 0, 0. For the AND operation is 0, right? 0, 1 is also 0. 1, 0 is 0, and 1, 1 is 1. So here have a sense amplifier, and you will compare the voltage between the reference voltage and the bin line. If the bin line voltage over the reference threshold, it means the result is 1. And if the voltage, the bin line voltage here below the voltage reference, it means the result is 0. So how to do that? The bin line, for example, here it's 1, it's 1 times 1 in the by the SRAM cell, 1 times 1, and we expect the result is 1, right? How to do that? You will pre-charge the bin line, pre-charge the bin line, and turned the mouse on here. The wall line will be turned on, and then if the bin line discharge very quick, if the bin line discharge very quick, it means it's 0. And if the bin line discharge very slow, it means the two content is 1, 1. So the bin line discharge very slow. So the amplifier will sense the bin line here, the voltage higher than the reference. So the result is 1. So here, we could use this to implement the logical operation by the SRAM, the AND operation and the NOR operation. And this slide introduces the matrix vector multiply using SRAM with capacitor. And how to implement that? The first step is map the SRAM content, the A matrix to the SRAM cell, here. And the voltage in is the input X, and the result, we can get the result by this field, the voltage to get the result. And the step is that map the A to the SRAM cell, right? The matrix to the SRAM cell here. And the map the X to here have a capacitor. This symbol is a capacitor. So the map the X to the capacitor, the voltage to the capacitor. And the first step is the step one capacitor charge to input value. It means the one this circuit to be connect to turn on, and the voltage will charge the capacitor. And step two here to be turned on. And if the SRAM cell is zero, uh, here this line is the bit line bar connect to the MOS. So if the SRAM cell is zero, the MOS will be turned on, and the capacitor will connect to ground. So if the SRAM cell is zero and the binline bar connect to the MOS, and the MOS to be turned on, and the capacitor, the charge will be drained to the ground. So you will lose the charge, right? So in this way, so yeah, in this way, if the X is zero, if the voltage is zero, the charge sensed here from the V out one will also be zero, right? Because the X is the voltage, because no charge in this capacitor. And if the X1, X2 here is high voltage, is a high voltage, and the SRAM cell is zero. We want the result to be zero, right? Because zero times one, we want the result to be zero. So if the A11 is zero, the MOS here need to be turned on, and the charge from this capacitor will be drained to the ground. So we could not sense the charge from this situation because the A11 is zero. If A11 is one, this MOS is off. So even the step two connect this circuit, and the capacitor also keep the charge. So we could sense the content. Yeah, right. So in this way, we could do the binary matrix multiplication by SRAM, and to get the result, right? It's the analog binary matrix operation. And yeah, this is a charge base. The SRAM is a charge base. And next, I will introduce the resistance base. The resistance is how much a material upsets the flow of the electric current. And resistance R is defined as the ratio of the voltage V across it to current I. R is equal to the V divided by the current, the voltage divided by the current I, right? And the conductance G is the inverse of the resistance here. So follow the Ohm's law. I is equal to the G, the conductance, times the voltage V. So have this, we could leverage this formula. We could use this formula to implement the multiplication. And yeah, this slide show the resistance-based memory device have IERAM, PCM, the STT, and RAM. All of them use the resistance state to store the information and how to read the data. We could apply a small voltage. For example, the conductance, the value is we program the memory cell change the conductance. So we store the conductance, the G, on the cell, and we apply a small voltage, and we can sense the current, to know the results on it, to know the data inside the cell. So at least we could do matrix vector multiply by using the resistance memory. And we use two characteristic. We use two law. The first one is Ohm's law, and the second one is Kirchhoff current law. Here, at the right hand side is the circuit layout, have the resistance on it, have 4 resistance, and we map the matrix A to conductance value to program the resistance to conductance value. We program it, change its state, program the conductance value, map the matrix A to the conductance, and so G11 here is the A11, G21 here is A21, G12 is A12, and we map the input, the X, to the read voltage, So follow the Ohm's law. We expect here this point will be G11 times the voltage, the V in 1, right? So actually, back to the formula, is A11 times the X1 here. And follow the Kirchhoff current law, the current out here is the summation of all current, So here, the result, the I out, the result, the B1 result will be the B1 result will be the A11 times the X1 and the A12 times the X2. So we could follow these two laws to do the multiplication and accumulation to get the result and do the operation inside the memory. We don't need to move the weight to the CPU, to the processor. We just need to program, store the weight on the resistance memory, and just apply the input, apply the voltage to the memory, and then we could get the result. This is the analog in memory computing by resistance memory. Yeah, the key concept is use these two laws to do the MAC operation. Okay, so yeah, recall that. Today we introduced the systolic array and the in memory computing, and since in that is because the volume architecture suffer from the memory bottleneck and the high energy data movement. So have two specialized hardware to make the machine learning operation to more efficiently. The systolic array, the key idea, the most important thing for the systolic array is load data once, and each processing and the data will propagate, go through all processing elements, reuse the data many times, so you don't need to communicate with the memory. You don't need a lot of communication. You don't need a lot of data movement between the memory and the processor. And in memory computing, the previous approach, we move the data from memory to the we move the data from the memory to the processing units to do the operation and write back the result. And in memory computing, there are two type of implementation. The digital implementation is just add processing unit inside the memory, and you can do the operation inside the memory, and or uh, use the material characteristic to do the make operation and follow these two laws. Okay, so in this way, yeah, remember at the beginning of this course, we showed this slide. The memory movement consume a lot of energy, right? Because if you need to move data from the DRAM, it need consume a lot of memory because the processor and the DRAM, they are two different chips. So the operation inside the chip is consume less energy. And if you need to move data between two chips, you will consume a lot of energy. So in this way, the systolic array and in memory computing, we could reduce the data movement operation to make the machine learning operation could be more efficient. So yeah, that's the slide. Have any question for today's class? Okay, if no question, class could be stopped here. Thank you.